In this video, we're going to describe organometallic carbon-metal bonding in terms of orbital interactions between the carbon on the ligand and the metal d orbitals. And we're going to start with simple alkene metal bonds. In this case, what we have is an sp3 hybridized carbon. So an sp3 orbital on the carbon and various substituents off that carbon center. And we can think of it as the lone pair in this sp3 orbital donating into a metal-based d orbital in a sigma type fashion. So for example, we can think about this donating into a metal dz squared orbital. Although we could also think of it donating into a dx squared minus y squared orbital in a sigma type fashion. Here, your interactions are between your metal d orbital and the carbon 2sp3, forming a bonding in an anti-bonding type orbital with the two electrons in that bonding type orbital, which is a sigma bond. This type of bonding motif is typically reactive. The reason that it's reactive is because you only have one type of orbital interaction that's stabilizing the overall metal Cr3 type bond, that sigma bonding type interaction. Because they're reactive, they're often found as fleeting transient intermediates in organometallic reactions. But because of the reactivity, it also makes it an important bonding motif because this metal carbon single bond to an alkene is reactive, and it can lead to a lot of interesting chemistry downstream from the metal carbon bond. Metal carbenes form another important class of organometallic compounds, and these have the general Lewis type formula of a metal double bound to a carbon with two R groups associated with that carbon. There are two types of bonding interactions that are important in stabilizing these metal carbene compounds. One is a sigma bonding interaction, where you have your sp2 type orbital on the carbon, donating an electron pair into a metal d-type orbital in a sigma type fashion. And this time we'll draw this as a dx squared minus y squared. So you have a sigma type bond. The other important interaction is the carbon p orbital on the carbene bonding to a metal d orbital in a pi type fashion. Depending on the energetics of the p orbital, you can have two different types of metal carbene compounds, so-called Fischer carbenes and Schrock carbenes. With a Fischer carbene, the energy of the metal pi type orbital is low relative to the carbon 2p orbital that's going to form that pi type bond. Schrock carbenes are the opposite, where the energy of the metal d orbitals that's going to bind in a pi type fashion is now greater in energy than the carbon 2p orbital on the carbene. If we look at the bonding interactions making up the metal-carbene bond, what we find in both cases is that the filled sigma-type orbital between the metal d sigma type of atomic orbital and the carbon 2 sp2 hybridized orbital is a carbon-dominated orbital. If we look at the Fischer-carbene and the pi bond, we find that the occupied HOMO, being closer in energy to the metal, is a metal-dominated orbital, while the LUMO is a carbon-dominated orbital. In contrast, in the Schrock-type carbene, the HOMO is a carbon-dominated orbital, being closer in energy to the carbon 2p orbital, while the LUMO, the pi star, is a metal-dominated orbital, being closer in energy to the metal d pi type orbital. This gives the carbon character completely different reactivity in Fischer-type versus Schrock-type carbenes. In the case of a Fischer-type carbene, the carbon atom is electrophilic. The orbital that's dominated by the carbon is an unfilled LUMO, it's the pi star type orbital. In contrast, the carbon atom in a Schrock-type carbene is nucleophilic. The carbon-dominated orbital is the HOMO in this case, so it's a nucleophilic orbital. Different types of carbenes will yield a Fischer-carbene versus a Schrock-carbene. In Fischer-type carbenes, the R group off of the carbon on the carbene are typically pi donors. In contrast, for Schrock-type carbenes, the R group are typically alkyls or hydrogens. If we look at the metals, then for Fischer-type carbenes, these are typically middle to late transition metals, while Schrock-type carbenes are typically made up of early transition metals. The metals are typically in low oxidation states for Fischer-type carbenes and high oxidation states for Schrock-type carbenes. Finally, the ligands about the metal center other than the carbene-type ligand are typically pi acceptor ligands. In the case of Fischer-type carbene metal compounds, while in the case of Schrock-type carbenes, these are typically chlorides, CP-type ligands, and alkyl-type ligands. One can also form organometallic compounds between a metal and an alkene or an alkyne. And in this case, we're considering these metals binding in to the alkene and the alkyne in this type of fashion. If we look at the pi system on an alkene, we can look at the pi and the pi star type orbitals. So the filled pi and the empty pi star. The pi looks like this and will donate into the metal center in a sigma type fashion. Contrast the pi star which looks like this, will accept electron density back bonding in a pi type fashion. We can look at the orbital interactions. Between the sigma and the pi type interactions. Where we have the sigma here, and this is from the alkene donating in a sigma type fashion, while the pi type orbital is due to the metal, the two electrons in the metal d pi type atomic orbital back donating in a pi fashion. So we can draw this interaction out. So drawing out the orbital interaction over here for that pi back bonding, you have your metal and it's donating electron density into that pi star on the alkene. So into the alkene's antibonding type orbital. This is going to influence the nature of that carbon-carbon bond. In the case of weak metal back bonding, we can draw the bonding interaction like this, where all we have is that pi donating into the metal d sigma type orbital in a sigma type fashion, and we have a true carbon sp2 hybridized orbital. In the case of strong back bonding, what we're essentially doing is we're putting electron density into that pi star orbital and breaking the carbon-carbon bond. So we can think about this as the metal now forming bonds to those two carbon atoms, and these carbon atoms being nominally sp3 hybridized now. And you would see an elongation in that carbon-carbon bond as back bonding increases. If you have ligands that have multiple carbon-carbon double bonds, we have to introduce a concept called hapticity to differentiate between different bonding modes. And what we do is we symbolize this with the Greek letter hapta, and then some number associated as a superscript to that hapta, where n equals the number of carbon atoms bound to the metal center. As an example, we can look at iron bound to a butadiene ligand. So an iron tricarbonyl bound to butadiene. Here, this is a hapta 4 because we have these 4 carbon atoms bound in to that iron center. This can react with HCl forming this species, here, where now it's bound in a hapta 3 fashion because we have these 3 carbon atoms bound in to that iron center. Cyclic hydrocarbons with aromatic pi systems can display varying degrees of hapticity. So for example, with your CP ligand, this can bind in a hapta 2 fashion. More commonly, it binds in a hapta 5 fashion. It can also display hapta 3 and hapta 4 type binding, depending on how many carbon atoms it gets bound to. With benzene, This can display up to haptic binding, but other hapticities are possible. There are a large number of other ligands that are typically associated with organometallic compounds and associated with organometallic chemistry. We're going to discuss two of these, dihydrogen and the nitrosyl ligand. So with dihydrogen, H2 is acting as a ligand, and it binds to a metal center in a similar fashion as an alkene in that type of manner. In this case, we refer to that H2 ligand as a dihydrogen ligand, and we typically put it in parentheses to distinguish it from a hydride or a dihydride type ligand, where you would have two H minuses binding into the metal center. The orbital interactions are the same as with an alkene compound, where you have a sigma type orbital that looks like that, and you have your sigma star that looks like that. So here, these will bind to sigma type metal d orbitals, and these will bind to pi type metal d orbitals. So if we have the two electrons in that H2 sigma, those will donate into a metal like that, while filled metal d pi type orbitals will back bond into the sigma star on the H2 ligand. Something to point out about dihydrogen ligands is that H2 is a very poor ligand. Dinitrogen, N2, which we typically think of as being an inert gas, will preferentially bind to a metal center over H2. So let's draw out a reaction involving some transition metal plus H2 forming a metal dihydrogen compound. The localized nature of the two electrons in that sigma orbital means that this sigma interaction with the sigma on the H2 donating into the acceptor orbital on the metal center is very weak. So this is a very weak interaction, and subsequently it forms a very weak bond. Most of the stabilization of a dihydrogen compound comes from the back bonding of the metal center into the sigma star. So this back bonding is what drives H2 coordination. However, there's a fine line between forming this dihydrogen compound and it going all the way and forming a metal dihydride. So the dihydrogen complex, and here we have the dihydride complex. You have to have enough electron donation from the metal center into those pi stars that you can stabilize the dihydrogen complex, but not so much back bonding that you dump a huge amount of electron density into that sigma star orbital, effectively breaking the HH bond and forming the dihydride complex. So you need enough back bonding to stabilize it, but not so much back bonding that you break the HH bond. The last set of complexes that we're going to talk about are metal nitrosyls. So the metal NO complex. And although NO is not an organometallic ligand, it's often associated with organometallic chemistry. NO is unusual in that it's a stable radical species. So NO has 11 total valence electrons associated with it, so an odd number of electrons. It differs from O2 in that it has one less electron in the pi star orbitals. So it has one electron in its pi star orbitals. Because of this, NO can bind to a metal center in one of three different oxidation states. It can bind to it as NO+, it can bind to it as the neutral NO, in which case we'd call it an NO radical, and it can bind to it as an anion, NO-. Depending on the oxidation state of the NO ligand, it can either bind in a linear or a bent fashion. So it can bind either like this or like that, where here the metal nitrogen oxygen bond is approaching 180 degrees, while here it's much less than 180 degrees. In the case of NO+ or NO dot, it can bind in a linear fashion, while in the case of NO-, it can bind in a bent fashion. And we can rationalize this by looking at simple Lewis structures. So here, in the case of a linear molecule, NO as NO+, would have a Lewis dot structure that looks like this, while in the case of neutral NO, it would look something like this. In the case of NO-, the Lewis structure would look closer to this, where that lone pair that's now formally on that nitrogen would cause this to undergo a bending and deviate significantly from 180 degrees. The reason for the multiple oxidation states that NO exhibits is because it's an example of something called a non-innocent ligand. A non-innocent ligand is just another name for what you would call a redox active ligand, meaning that you can do electron transfers to and from that to a first approximation. And the reason for this is because that pi star orbital is comparable in energy to the metal 3d orbitals. And because of that, you get strong covalent overlap between the NO pi star and the metal 3ds. Because of this, it's incredibly difficult to do oxidation state and electron counting assignments for metal nitrosyl compounds. And because of this, a notation has been developed. Where in brackets you'll put the metal, the number of NO ligands, and then a number n, where n equals the sum of the metal d electrons plus the unpaired electron from your NO ligands. So, for example, in this complex here, which contains one NO ligand and an iron 2, we would signify that this is an iron NO7 compound. 6 d electrons from the iron 2, the 1 electron from the NO ligand, so it's an iron NO2-7 complex. Doing so eliminates ambiguities concerning the oxidation state of the NO ligand. One could obtain structural information on this species, determine whether that NO is forming a bent or a linear coordination moiety, and then estimate what the oxidation state of iron and the NO is. But the better description, because of the high covalency of the iron-NO bond, is really this iron NO7, as opposed to calling this an iron 2 NO dot or an iron 3 NO minus species, for example.